Okay, so we'll go over background information you need, and you need to have this in your logbooks. Not every single word, but some kind of summary. So this is the basic structure of a capacitor, and I'm gonna guess you probably haven't done it in lecture yet. So you have two conductive plates, two parallel conducting plates. Yep. And there's a distance, and what happens is when you connect the battery, some temporary current flows, and whenever a current is you use little I, so we define I as sort of like a current that has some time dependence. And in this case, it's a transient current because charges flow, but they can't cross the barrier here. They can't get across. So when it fills up with charge, the current stops because this thing ends up being like its own battery. So you see plus Q, plus minus. So that a charged capacitor looks kind of like a battery. So now, since the voltage here will eventually equal the voltage of the battery, then there's no current because there'll be no more delta V. And the other thing to keep in mind is there's no net Q. It's always zero. So we'll just throw out here. This is the definition of capacitance. And so if it can hold more Q, then it has more capacitance. So capacitance is about how much charge the capacitor can store, and how much voltage is required to force that in. So if I need less voltage to push in the same amount of Q, then we say it has this a larger capacitance. So we can also say that capacitance, we can define it physically, area divided by the distance, and we have the permittivity of free space. So we can relate the definition of a capacitor to its physicality, and it makes sense here. You see, if we make the area bigger, we can get more Q in there. If we make the distance between them smaller, then that would change the electric field, which is expressed as volts per meter. And you see the volts here. And you can imagine there's an electric field in here from other discussions we've had. And a capacitor stores its energy in electric field. And now we need to make the units match, coulombs per volt. So we need this fudge factor called the permittivity of free space. And then the units are farads. And because a farad's a big ass thing, 1.5 farads, we use microfarads. These little guys are actually going the way of the dodo and themselves. We use even smaller ones, but say this 470 microfarad is about as big as this little rectangle here. And you see 1.5 farads, and basically 470 micro. So this is like 3 times 10 to the 5th bigger. Even though it's physically not that much bigger, it has to do with different materials inside. But you'll learn about that in lecture class. So we need some basic circuit theory. And I had tried recording this earlier so you can see that there's stuff here, the writing I had been doing. Let's see if I can get rid of it. Because, in fact, I realized when I went to the next slide, I was jumping the gun. Well, we need that. So this is a basic circuit. You need at least one conducting path from the battery and back to the battery. Well, I say plus to minus because it could be a power supply. And if you remember a pre-lab you did, how can I make what can I do to make a light bulb light? Well, I run a wire from the battery to the light bulb, and then from the light bulb back to the battery on the other end, so we get a continuous conductive path. All the current that leaves has to come back, and we have this thing called Ohm's law, and so we say that these circuit elements, there's some kind of R total among them. And that square I had drawn up was like there's some black box. So this has some R total. And so if we multiply R total and I total, we should get the voltage of the battery. Okay, so then this is a series circuit. And a series circuit has only one conductive path. And the current is the same everywhere. And this means that that the sum of the voltage drops. So in order for current to flow, if you want to have current not be zero, you have to have delta V not be zero. So the first thing you do is put a battery. So also we need to go from voltage battery down to zero. And so we can't go to zero here, for example, because if we did, there'd be then there'd be no more delta V to the rest of the circuit. So each one of these things has a voltage drop across it. And if we sum up those changes in voltage across each one, it has to equal the battery. So then we go to the other kind of circuit. It's called a parallel circuit. And with the parallel circuit, we have multiple current paths. We always assume that there's no voltage drop across a wire. So that means that everywhere along the top here at B, C, and D has to be at the voltage of the battery. Every place at F, G, and H, VF, VG, VH has to be at zero. And we see that this also, A and B is this point A is at VB, and this one here is at zero. So that means that everybody has the same delta V, same voltage drop, but now the current is not the same everywhere. All we have is the basic rule that all that leaves has to come back. So you see it splits here, I1 goes there, I2 plus I3 continues, I2 goes down there, I3 continues, I3 comes down, and then it joins I2 plus I3, and then I1 joins those two, and that equals the total, and they go back. So I paused it for a moment because I'm wrestling with the idea of should I go to the experimental technique, but you need these rules of combination to understand how the experimental technique works. So to subscript or not to subscript, and why do I care? Well, what happens is here, because I can apply this definition to any capacitor, so I can apply to C1 equals Q1 over V1, and C2 equals Q2 over V2. But we remember from the parallel circuit rule that we don't, it's the same V for both of them. So that's important. So then that allows us to, and this is the easy one, this allows us to come up with the rule of combination because we can then add together. Oh well, let's do it. Yeah, the voltage drops are the same, and so yeah, how do we? I'm going to pause for a moment. So I was trying to think of a way of relating this rule of combination with the voltage drops and the currents and all that, and I just for the life of me can't think of it. The standard way to say it is that since we know everybody has the same voltage, we can attack the problem by saying, okay, what's the total Q? And the total Q is going to be, of course, the Q on each of the two of them. And, oh yeah, and then because they're in parallel, see, positive to positive, negative to negative. So the bottom line is that you're effectively making the plates larger. And so even at that point, big whoop, because we could have been stuck with C1 V1 and C2 V2, but because of the parallel combination, we don't have to do that. So we can pull out the common term. And so we also know then that, what else do we know? Oh yeah, so then we say Q, it's the Q. Well here, let's just do the next slide. And C equivalent, yeah. Oh, yeah, right. So Q total, of course, is going to equal C equivalent times V, because it's the same V for everybody. On there it is there. I just didn't practice before I started recording. And so we can just eliminate the common term, so we're left with this. It's one of the things we're going to verify in the lab, or you're going to try to verify. And that's just a summary. So how do you do two capacitors in series? Well, in two capacitors in series, it turns out that they end up with the same Q. Whereas in parallel, remember, they each had their own Q. But now in parallel, a series, they end up with their own. And the reason is because as the transient current flows, eventually they fill up, right? So when the smallest one fills up, let's say C1 is smallest. So as soon as C1 is full, then the potential here equals the battery potential, and no more current can flow. So even though C2 wants more charge, it can't get it. So they both have the same Q. So then what we're going to do is we're going to take advantage of this right here from the series circuit. The voltage drops have to equal the battery. So and also that we have the same Q, so no subscript is necessary there. So then when we try to add them together, we end up with, we're adding the two voltages together. And just as before, the V itself equals total Q over total C. And then we can eliminate the common term again. And so this is how we add together two capacitors. And when you only have two, you can come up with an equivalent equation for two. So we can create a common denominator, C1 times C2. So it becomes C2 plus C1. And then, of course, we have to invert it. So, because it's 1 over C, so this would be C1, C2 over C2 plus C1. It doesn't matter the order. Okay, and then, well, we're left. Then it's the summary once again. Excuse me. So I'm going to pause this one more time. And by the way, and I was just checking through the manual. So you see here, this is equation 10. So let's go back here for a moment. So we got, I'll rewrite it. C equivalent equals C1, C2 over C1 plus C2, and equation 10. Let's see what page. Of course, it can't see it. Page 18. Well, that's dubious. Looks it's page 18 on the bottom. So page 18 of the manual, and in my case, it's page 3 of the PDF of the manual. And then, oh yeah, and let's relate. We also need the series. And my recollection is that it's equation 5. Yup. And the manual has sort of the same build up. I don't think they do as good a job as I do, but I guess I'm prejudiced. So this is equation 5 from the manual. Okay, so now we want to get into the experimental technique and how we're going to determine. So remember, our goal is to measure, we're measuring 2 unknowns, well, 4 unknowns actually. We're going to measure 4 unknown capacitances. And okay, so that may not be exactly what you think, because what happens is part of what we're doing is verifying, right? So we're gonna verify series and parallel combinations. And so what we're going to do is we're going to measure the total capacitance of the series and parallel. So we're going to measure, and we have, remember, we have a known sort of test capacitor, and then we were given C1 and C2, and then we're going to have C1 parallel with C2, and then C1 series C2. So at the end of the day, that's 4 different unknowns. So what you see here is this is figure 8 from the manual, and I've changed it, and we're going to use it in this form, C-test, to emphasize that what we're doing in this part is we're developing a testing apparatus and a testing technique for doing our measurements, because we want to approach this as good engineers, good scientists. So how are we going to determine C-test? Okay, how do we determine C-test? So what we know from basic circuit theory, that there's going to be a delta V from our known and a delta V of C-test, and delta V of C plus delta V of C-test has to equal to voltage of the battery. And So that would be, we have to remember that C equals Q over V. So the voltage on C is going to be V equals Q over C. So that's going to be Q1, or just Q, right, over C plus Q of C test over C test. But we also know that the Q is the is the same in a series combination. So I mean, remember this is, oh yeah, that's what I already said. It's series, so that equals V battery. So what we can do is, since there is no subscript anymore, we see that, you're right, so that we know that the V measured here is going to be, give me a minute. Well, I must say that I got a little hung up in this calculation, and so I sat down with some scratch paper to try and figure this out, and gosh, it took me a couple hours. Unbelievable. Okay, so this is the basic circuit theory. The battery, the sum of the voltage drops of the circuit has to equal the battery. So what we're interested in is somehow getting an expression for C test. So we know that we have C equals Q over V. And so I know that then CT equals Q over V test, which happens to be V. Now, one thing here is that Q, we don't know Q, we have no way of measuring it. But I just wanted to quickly point out, just like in doing the series calculation, we could, let's see, so that would mean this could be Q across C over C itself plus Q across C. Well, you see, it's the same Q because they're in series. Across C test equals Q and C equivalent, the total. And I was trying for the longest time to come up with a way to, because what we're trying to do is we want to get equation 19. And that equation 19, funny, is not in front. Oh yeah, here it is. So we're trying to derive equation 19, which is CT equals C times VB over V minus 1. We could do that again. V battery over the voltmeter. So anyways, you know, it's just a few lines at the end of the day, but everything is easy when you know the answer. So, and to remind you that this here VCT is equal to, the equivalent is V from the voltmeter. So I have this idea that I want to get CT on the left, so I thought, okay, I'll do this. V equals, and then it's going to be the V battery minus VC. And I thought, okay, I need to make an expression for VC. So I already know that it's where'd it go? Here. It's right here. So then I went ahead and I substituted that in. So I have because I don't know what VC is, so I know I have to get rid of it. I don't have a way of measuring it, or I could, but I didn't. I just know that from the manual, for example. I mean, if we were doing a real experiment, we'd mess around with this, so we'd get two different voltmeters, and also it's really not the right way to measure capacitance. So, oops. I goofed there, went a little too fast. So then we get Q over C, but now we're back, we're in a position where, gosh, we have to do something about this Q. But because all the Q's are the same, we can put in any, so if Q equals CV, we can use CT times the voltage across CT, or the C equivalent times the battery voltage, etc., etc. So we can choose whatever we want. So I'm going to choose to use the minus CT times V. And so now all of these things are things that I know or can measure, except one, the CT here. So I'm going to pause once more for a moment. All right, so you can just see that I got rid of a couple intermediate steps, and I moved those up there. So now you can see how there's CT, so we got to get it on one side. So I'm going to move it over to the left of the equal sign. So I just have it, and then I'll get a plus sign. So it's CT V over C. And so the VB stays, and then I got to bring the V over here, and minus V. So now I just have to multiply both sides by C over V, and then when I do that, you see that'll cancel out the V over C. I'm left with CT equals C over V times VB minus V. And then if I can distribute the 1 over V equals to C times V over B over V minus 1. And this is nice. The reason to do that is because then I only have to plug in each number once. That's all. Nothing special. So pause again for a moment. All right. So you didn't notice any difference. So we have C test equals C times VB over V minus 1. And so let's see what's next. So we take the measurements. Now we discuss the measurements, and let's pause one moment again. All right, back again. Now during class, we went over this idea about we have to take the measurement 3 times, because every time we close this switch, we notice that the voltage just decays on the voltmeter. So that's why we take it 3 times. And then also we have to add some circuitry there. for discharge, remember we had to put in the 2 push buttons. Well, the part about the push buttons is something we learned in the discovery process when we actually took data. So just for the point of background, I want to finish the thought of measuring 4 unknowns. So what happens is we're going to transition now to this figure. So what we're actually going to be doing, remember we had CT from the previous slide. What we're going to say now, this is actually the device under test. Engineers love this one. Device under test. So there's the first device under test is going to be C1. The second device under test is going to be C2. And then it's going, I don't remember it. Oh, it says parallel. All right. So it's going to be C1 and C2 in parallel. And so we should just say that C1, C2, and then it's going to be C1 and C2 in series. And you can just literally think about it as different things that you're dropping inside the box. The thing to remember is that your test system here, the test setup, is always about 2 capacitances in series. So every time you calculate a capacitance here with this equation 19, you're just measuring the total capacitance of the system. You don't know. You in a way you can say I don't know what it's made of or not, but all you're doing is measuring the total. Now you have a proposal of 2 equations that and I believe it was 5 and I don't remember the other one, but the parallel and series. So you can take the values of the capacitances that you determined and combine them and come up with a calculated capacitance and see how much different they are. So if they're within plus or minus 10%, then we know that the rules apply. And that's what we're doing. It's like theory testing. We have a proposed equation or a proposed theory, and we want to test it against experiment. Okay. Wow, this turned into longer than I thought it would. But it's about what I usually take in the beginning of a lab class.